Chapter 8, Think and Solve. Number 44. Diameter of the base of a tapered drinking cup is 6 centimeters. The diameter of the mouth is 9 centimeters. It travels in a circle as the diagram is given. Which end the base of the mouth rolls faster? Well, the wider end is rolling faster, and that it has to cover more territory in the same amount of time. And given the diameters, if you think about one rotation of the cup, that basically it's rolling on the distance it rolls when it goes around once. The distance it rolls is the circumference. So the bottom is rolling a distance of 2 pi times 6 centimeters. The top is rolling a distance of 2 pi times 9 centimeters. And so in the same amount of time, the top is traveling basically 50% more than the bottom is. Number 45, to tighten a bolt, you push with a force of 80 newtons at the end of a wrench of 0.25 meters from the axis of the bolt. What torque are you exerting? Now, he doesn't actually specify it. There's not enough information explicitly here in order to answer this question, but we have to assume, and he's assuming, that you're pushing perpendicular to the wrench. So I got a wrench right here, and you're pushing perpendicular to the radial vector right here. So 80 times 0.25 meters gets you, that should be 20 Newton meters. It's the magnitude of the torque. Now you move your head inwardly to be only 0.1 meters from the bolt to achieve the same torque. Show that you exert 200 newtons of force. Well, I'm applying 20 Newton meters of torque. And so now, since we moved in, we have a smaller radial vector, and therefore we have to apply a greater force. And if you'll notice, 200 times 0.1 is 20, so we get 20 Newton meters, and so we get the same torque. And do your answers depend on the direction of the push relative to the direction of the wrench handle? Absolutely. Because, again, torque is R cross F, even though he doesn't state it explicitly here. It's the radial vector times the force, and so direction matters. If I push in this direction, I'm going to get a torque that is being applied. The torque vector will be pointing towards me. If I push down, the torque vector is being pointing away from me. Yeah. And if I push directly into it, I get absolutely no torque whatsoever. And probably at this point we've done the door demonstration, so just sort of relate back to that in your notes. Number 49, trapeze artist rotates around once each second while sailing through the air and contracts to reduce her rotational inertia to 1/3 of what it was. How many rotations per second will result? So this is a conservation of angular momentum. Angular momentum, there's the formula near the top of that page that says mvr, but the other way of looking at it is it's I times omega. Just like linear momentum, P equals mv. The rotational analog is L equals I omega. And so as I goes down, omega goes up. And so if she reduces her rotational inertia to 1/3 of what it was, then the angular speed or angular velocity must be multiplied by a factor of 3 to balance out. And so we end up with, well, it's basically, she was rotating once each second, so now she'll rotate 3 times each second. And that is it for the Chapter 8 Think and Solve.